Okay, let's get started. Once again, we are in Math 152, Section 4, Professor Ellis's course. And your SI Jack Quirk. And today I'll be showing you some examples of polar calculus, which is working integrals, derivatives, arc length, etc. with polar coordinates. So, start off with a review of how polar coordinates work. Again, we have to remember that x is equal to r cosine theta, y is equal to r sine theta, and the tangent of theta is equal to y over x. Now, a side identity based on the derivations of x and y, we know that x squared plus y squared is equal to r squared. So these are all we really need to do to convert any given Cartesian equation into polar coordinates. Let's take a look at that. Say we have the equation r squared is equal to 5, a polar equation. R is equal to the square root plus minus square root of 5. Just a circle. So, how do we get this circle into its respective Cartesian equation? Well, we make our substitutions for r. 5 is a constant, there's nothing we can really do with it, but we already know that r squared is equal to x squared plus y squared. So x squared plus y squared is equal to 5, which recognizes the equation of a circle. Now, if we want to get this into, let's say, y in terms of x, again, relatively straightforward. Y squared is equal to 5 minus x squared. Take the square root of both sides. And we're left with y is equal to the square root of 5 minus x squared. So either of these two would work for our Cartesian equation. It's really just a matter of what's being asked for. Now, let's take another look here. Say we have, let's separate this out here. 1, we have problem 2. And let's say that we have theta is equal to pi over 3. So our knowledge of polar coordinates tells us that this is going to look like a line when we're done with it. Just all the points that lie on the angle theta is equal to pi over 3. So, in order to make this one work, we remember that we'll take the tangent of both sides. We have tangent theta is equal to tangent of pi over 3. And we know from our identities that tangent theta is equal to y over x. Tangent of pi over 3 comes out to a constant. We've got that. So, the tangent of pi over 3 is, let's see here, pi over 3, sine over cosine, sine pi over 3, we're at 3 over 2, and the cosine divided by 1/2, this comes out to root 3, and that will be equal to y over x. So our Cartesian equation, y to x square root of 3. Like we said before, just a line with a given slope. Nothing too revolutionary about that. So we're going to have, let's do 2 more of these conversion problems. It's important to have a complete understanding of just this baseline. Alright, our third problem, we have x, y is equal to 4. And we want to get this in terms of a polar equation. So, what do we do here? Well, we sub in for x and y in terms of r and theta. So x is equal to r cosine theta times y, which is equal to r sine theta, and that's equal to 4. So we're going to divide our cosine and sine theta over and get this as r in terms of theta. So we'll have r squared on the left is equal to 4 times, and now we're going to do a little bit of simplification here. 1 over cosine is secant, 1 over sine is cosecant, so we'll have 4 secant theta cosecant theta. And to get this in terms of r, we just say r is equal to the square root of 4 secant theta cosecant theta. Again, relatively straightforward as long as you know your identities. Most of these problems shouldn't give you much trouble as long as we can remember this top portion here. So, one more conversion problem for you. We'll have 4y squared is equal to x. And again, let's get this in terms of polar coordinates. So, y squared is going to be, well, 4y squared. When we sub in y is equal to r sine theta, will mean 4r squared sine squared theta. And we set that equal to r cosine theta, which is x. This r and this r cancel out. Divide the sine theta over, get it in terms of, get r in terms of theta. So we will have 4r is equal to, and again we'll do our simplification now. Cosine over sine is cotangent theta. And 1 over sine is cosecant theta. And to get this in terms of r, just divide 4 over cotangent theta, cosecant theta, r divided by 4. So there you have it. Nothing too tricky about that. Again, I can't really stress enough knowing your polar equivalence identities. This top portion here is invaluable when we're talking about polar coordinates. And once you have enough exposure to them, they'll just sort of become second nature. Okay, so we're going to move on to a little bit of calculus. Specifically, we're going to calculate areas under polar curves. So let's take a look at this particular curve. We have the question, r is equal to e to the negative theta over 4. And we want the area under this curve based on the interval pi over 2 is less than or equal to theta is less than or equal to pi. All right, now when we run these sorts of calculations, again, it's important to keep in mind the derived area formulas that we've already solved for. So the area under a polar curve is going to be equal to the integral from your bounds integration a to b of 1/2 r squared d theta. That's just an equation. We derived it in class. Commit it to memory. We can also solve for area using a similar integral, a to b, but this time we're going to have it in terms of theta. We'll have 1/2 f of theta squared d theta. Sorry about that. So again, these are just two expressions of the same exact thing. Typically, f of theta is equal to r. We solve for r in terms of theta, so that's how that equates. Okay, so let's see an example of this in action. We have our polar equation, r is equal to e to the minus theta over 4. So we can just plug that straight into our first area equation. We'll have the area under the curve is equal to the integral from pi over 2 to pi of 1/2 and e minus theta over 4 squared d theta. So before we go and solve this, let's simplify it a little bit, make it easier on ourselves. This is going to be equal to 1/2 integral pi over 2 pi e to the minus pi over 4 times e to the minus pi over 4 is going to be e to the minus 2 pi over 4, or e to the minus, not pi, theta, e to the minus theta over 2 theta. Okay, so we can evaluate this. We've learned integration with respect to e to the power, fairly straightforward. We have 1/2 times negative e to the negative theta over 2 divided by the chain rule equivalent of pi over 2 1/2. All right, and this is evaluated from pi over 2 to pi. All right, so 1/2 in the denominator, 1/2 out front, cancel out. So I'm going to take a look here. We have evaluating the integral minus e to the minus pi over 2 minus e to the negative pi over 2 over 2. So you're going to simplify to negative pi over 4. These cancel. Negative negative makes a positive. So our final answer is going to be e to the minus pi over 4 minus e to the minus pi over 2. So that one, pretty straightforward process. It gets a little messy towards the end with the numbers we were given, but nothing we haven't covered before. Just an application of the formulas I gave you at the start of this. Okay, let's take a look at another area. All right, so let's say we were given this equation. R squared is equal to 9 sine 2 theta. And we wanted the area for the interval 0 less than or equal to theta less than or equal to pi over 2. All right. So once more, we can just plug this into our first area equation. We will have the area under this curve is equal to, and we can pull the 1/2 and the 9 out because they're just constants. They'll just be multiplied back in at the end. So we'll have 9/2 integral from 0 to 2 of sine 2 theta d theta. Now, notice I didn't square 9 sine of 2 theta because r squared was already given in our equation. Excuse me. Okay, so we can integrate this sine value, no problem. We have area is equal to 9/2. The value is 0 to pi over 2 of integral of sine is negative sine of 2 theta by 2 sorry, allergies. Okay, so now we just evaluate this expression. We'll have 9 times the negative cosine of 2 pi over 2 here minus cosine 2 times 0 over 2. Okay. All right, this simplifies to 9/2 times, the 2's cancel. We have the cosine of pi, which is -1. However, we have a minus already in the numerator, so we just get 1/2 minus cosine of 0 is 1, so we'll have a negative 1/2, but minus is equal to plus. So again, we'll have a positive 1/2. So 1/2 plus 1/2, that's just 1. We have 1 times 9/2 equal to 9/2 is the area bounded by this curve on this interval. Okay, I think that's probably enough in terms of area. Again, as long as you remember the given area formulas, there won't be any problems. I mean, there's always hard ones out there, but we have the tools. So, last bit here. Let's find the arc length of the curve. R is equal to theta squared. For r is greater than or equal to 0, on the interval 0 is less than or equal to theta is less than or equal to 2 pi. Now then, the arc length formula in polar coordinates. Another important thing to remember. We have the integral bound's integration a to b times the square root of r squared plus dr d theta squared d theta. So, pretty straightforward. Just plug in what we've already been given. Since we're integrating with respect to theta, our bounds of integration will be values of theta, 0 and 2 pi, times the square root, and you get this in terms of theta, so r is equal to theta squared. R squared will be theta to the 4th, plus, and we'll evaluate dr d theta over here, which is just going to be 2 theta. So 2 theta times 2 theta is 4 theta squared d theta. Okay, so in this particular case, we can pull a theta squared out of our term. The integral from 0 to 2 pi of the square root of theta squared times theta squared plus 4 theta. Theta squared is simplified to theta. It's pulled out as root of 2 pi theta square root of theta squared plus 4d theta. And our experience will tell us that this is just a u sub. We have u is theta squared plus 4 du is equal to 2 theta d theta. So we'll pull a 1/2 out here. We'll have 1/2 integral 0 to pi u to the 1/2 du, which is evaluated 0 to pi u to 3/2 over 3/2, 3/2 times 1/2. 2's will cancel, and we'll just be left with a 3 in the denominator. Plug our u back in, we'll have theta squared plus 4 raised to the 3/2 over 3, evaluated from 0 to 2 pi. Plug this stuff in, we'll have 4 pi squared plus 4, all raised to the 3/2 over 3, minus 4, the 3/2 over 3. That is the arc length of this curve over the given interval. So that should do it for today. Again, as long as you know your formulas, this stuff is going to be pretty straightforward. I hope that clarified a few things for you. If you have any questions, feel free to ask. Thank you for coming, and have a good day.